Deep beneath our feet, something is stirring. Across the world, seismic sensors have been picking up an unprecedented surge in activity, over 15,000 tremors recorded in just 1 month. This isn't normal. While small earthquakes happen all the time, usually going unnoticed, this level of activity is extraordinary. It suggests that something is happening underground, something that scientists are scrambling to understand. The question is, what's causing it? Could it be magma shifting beneath the Earth's crust, signaling the early stages of a massive volcanic event? Or perhaps it's a sign of deep tectonic stress, building toward a major earthquake? Some researchers are even considering more exotic explanations, such as unknown geological processes or interactions between the Earth's core and mantle that we barely understand. One of the most alarming aspects of this seismic swarm is its unusual distribution. Normally, earthquake clusters are confined to well-known fault lines or volcanic regions, but this surge in activity is appearing in unexpected locations, places that have been geologically stable for centuries. In some cases, tremors have been detected in regions with no historical record of significant seismic activity, raising the possibility that new fault lines could be forming or awakening after thousands of years of dormancy. Seismologists have turned to satellite data, deep Earth imaging, and GPS monitoring to track subtle changes in the planet's crust. Some areas have shown unusual uplift, where the ground is rising ever so slightly, hinting at magma movement below. In other locations, vast sections of land are shifting in ways that defy easy explanation. Could this be the early warning of a much larger event waiting to unfold? Another possibility that has scientists on edge is the connection between these tremors and deep-sea seismic activity. Ocean floor sensors have recorded strange vibrations emanating from the depths, some of which don't fit the usual patterns of tectonic movement. Some researchers speculate that this could be linked to massive subduction zone activity, where one tectonic plate is being forced beneath another at a much faster rate than previously believed. If that's the case, it could mean a catastrophic megathrust earthquake is on the horizon. Then there's the question of what's happening beneath the Earth's crust at an even deeper level. Some geophysicists suggest that shifts in the outer core, where liquid iron generates the planet's magnetic field, could be responsible for some of this seismic activity. Recent studies have shown that the Earth's magnetic field is undergoing strange fluctuations, and some wonder if there could be a link between these anomalies and the surge in tremors. If the core itself is shifting in a way we don't yet understand, the consequences could be far more profound than just earthquakes. At the same time, researchers have been investigating the potential role of underground reservoirs, massive pockets of water, oil, or even molten rock trapped deep within the Earth. If these reservoirs are being rapidly drained or refilled due to natural processes, it could explain the sudden instability in certain regions. In fact, some of the tremors have been traced to areas where scientists suspect vast, hidden magma chambers exist, raising fears that we could be witnessing the slow build-up to a future supervolcanic eruption. There is also the possibility that human activity is playing a role. Hydraulic fracturing, deep drilling, and large-scale mining operations have long been associated with minor seismic activity. However, some geologists worry that these industries may be disturbing deeper fault lines than we previously realized. Could it be that our relentless extraction of Earth's resources has triggered something much larger than anticipated? Meanwhile, some of the world's most active fault lines, like the San Andreas in California, the Cascadia subduction zone in the Pacific Northwest, and the massive fault systems beneath Asia, are already under immense stress. If these tremors are a prelude to a major rupture, the damage could be catastrophic, especially in densely populated areas. Scientists are analyzing whether these swarms might be triggering a domino effect, where smaller quakes gradually destabilize larger faults over time. The problem is that while we can measure these tremors, we still struggle to predict what they mean. Are they harmless adjustments in the Earth's crust, or are they leading up to a disaster? The only thing we do know for sure is that something unusual is happening beneath us, and as the tremors continue, the urgency to understand them grows. And if history is any guide, the Earth has a way of reminding us that it is in charge. Across the globe, Research stations and seismic monitoring centers are operating around the clock, analyzing every tremor for patterns. Each shift in the Earth's crust tells a story, one of pressure, movement, and forces beyond our control. Some quakes are shallow, their origins barely a few miles beneath the surface, while others come from the depths of the mantle, where the heat and pressure are unimaginable. The variety in these quakes suggests multiple processes at work, possibly interacting in ways that we don't yet understand. Beneath the Pacific Ocean, deep-sea instruments have picked up mysterious, low-frequency vibrations. These signals don't resemble typical earthquake activity. Instead, they resemble something known as harmonic tremors, a type of sustained seismic energy often associated with magma movement. If volcanic activity is at play, it could mean that undersea volcanoes are becoming more active. This possibility raises further concerns, as large-scale underwater eruptions have the potential to displace vast amounts of water, triggering tsunamis that could devastate coastal regions. Some researchers are turning their attention to an even more enigmatic source of seismic disturbances, the mantle plumes. These massive upwellings of hot, buoyant rock rise from deep within the Earth, slowly making their way toward the surface. If one of these plumes is shifting or intensifying, it could be responsible for the swarm of tremors being recorded. Scientists studying Yellowstone, for example, have long suspected that a mantle plume feeds the supervolcano beneath the park. Could a similar phenomenon be occurring elsewhere, destabilizing vast portions of the crust? Meanwhile, anomalies in gravity readings suggest that something massive is shifting deep underground. Satellites equipped with highly sensitive gravimeters have detected subtle but measurable changes in Earth's gravitational field. These fluctuations might indicate the movement of large magma reservoirs, the shifting of vast subterranean rock formations, or even the collapse of hidden underground caverns. If an enormous chamber of molten rock is redistributing itself beneath our feet, it could explain the widespread, seemingly random tremors. Another unexplored avenue is the role of Earth's inner heat cycle. The planet's interior is not static, it churns, shifts, and convects as immense thermal energy radiates outward. If this natural cycle is undergoing a shift, even a minor one, it could lead to changes in tectonic activity on a global scale. Some geologists theorize that variations in heat flow from the core to the mantle could be responsible for sudden increases in seismic activity. If that's the case, it could mean we're witnessing the early stages of a long-term transformation in Earth's geological behavior. Adding another layer of complexity, recent reports suggest that some of these tremors coincide with unexplained electromagnetic fluctuations. These disturbances, detected by ground-based observatories and satellites, show irregular spikes in the Earth's natural electromagnetic field. Some experts speculate that these fluctuations could be tied to shifts in underground mineral deposits, particularly quartz, which is known to generate electrical charges under pressure. Others wonder if we are seeing the influence of cosmic radiation interacting with the planet's deep interior. Still, the most pressing concern remains: are these tremors a warning sign of something catastrophic? History has shown that major seismic swarms can precede devastating earthquakes. The infamous 2004 Sumatra earthquake, which triggered a massive tsunami, was preceded by an increase in smaller tremors in the region. Similarly, the 2011 Tohoku earthquake in Japan followed a period of heightened seismic activity. If the current surge in tremors is following a similar pattern, it could mean that the stress building up in Earth's crust is reaching a breaking point. The scale of this seismic event is what makes it so unnerving. These aren't isolated incidents occurring in just one region. They're happening across multiple fault systems, deep ocean ridges, and even in areas previously considered geologically stable. The global nature of these disturbances suggests that something fundamental is shifting beneath us. Yet, for all our advanced monitoring tools and scientific models, we are still largely at the mercy of the planet's internal forces. Tremors continue to be recorded, sensors remain active, and research teams push forward, determined to uncover the true cause behind this unprecedented surge in seismic activity. Whatever is happening underground, one thing is certain: it isn't over yet. Seismologists are now turning their focus to an unexpected variable: fluctuations in the Earth's rotational speed. While the planet's rotation is generally stable, it does experience minor variations due to complex interactions between the core, mantle, and crust. These fluctuations, known as length-of-day variations, have been linked to changes in seismic activity. When the Earth's rotation slows slightly, even by a fraction of a millisecond, it can alter the distribution of angular momentum within the planet, placing additional stress on tectonic plates. Could the current swarm of tremors be tied to a broader planetary shift in motion? At the same time, anomalies in geothermal activity are raising additional concerns. Thermal imaging satellites have detected unusual heat signatures emanating from unexpected regions, including areas that historically have had little to no volcanic activity. Some of these hotspots appear to coincide with locations experiencing the most frequent tremors. This suggests that magma movement, previously undetected, may be occurring beneath the crust at a much larger scale than anticipated. If this is the case, then we could be dealing with the early stages of a widespread increase in volcanic activity, not just localized events, but a global surge in eruptions over the coming years. Adding to the mystery, deep borehole sensors, drilled miles underground to study seismic activity, have picked up bizarre acoustic signals. These infrasonic vibrations are so low in frequency that they are barely perceptible to human ears, yet they carry valuable data about the movement of underground structures. Some scientists speculate that these signals might be linked to the collapse of subterranean voids, massive underground chambers that could be remnants of ancient magma reservoirs or unknown geological formations. If these voids are caving in under extreme pressure, they could be triggering seismic waves that ripple outward, causing the tremor clusters we are now witnessing. Meanwhile, geologists studying the ocean floor have come across another startling find: methane seeps that have become significantly more active in recent months. Methane is trapped beneath the seabed in ice-like structures called clathrates, and disturbances in the Earth's crust can cause these deposits to destabilize. As the methane escapes, it can contribute to both oceanic disruptions and atmospheric changes. If the widespread seismic activity is disturbing these deposits, it could have far-reaching effects, not just geologically, but climatically as well. Sudden releases of methane are known to contribute to climate instability, and if the current swarm of tremors continues, it could lead to an increase in these emissions. And then there's an even more radical hypothesis, one that pushes the boundaries of mainstream geophysics. Some theorists suggest that deep underground reservoirs of water, hidden miles beneath the crust, may be shifting. Research has shown that vast pockets of water exist far deeper than previously thought, trapped within mineral structures under immense pressure. If these reservoirs are undergoing movement due to tectonic stress, it could mean that the very composition of the lower crust is changing. Could this be part of a much larger cycle of planetary evolution, one in which the Earth's deep interior periodically reconfigures itself in ways we have yet to comprehend? As scientists scramble to make sense of the data, one thing is becoming increasingly clear: the planet is undergoing a level of seismic activity that defies conventional explanations. The question remains, are we witnessing the prelude to something larger, or is this merely a temporary fluctuation in the Earth's restless behavior? For now, the tremors continue, and with each new shake of the ground, the mystery deepens. Beneath the surface, another phenomenon is catching the attention of geophysicists: anomalous shifts in Earth's gravity field. Satellite measurements have revealed slight but measurable changes in gravitational strength over regions experiencing the most intense tremor activity. While these fluctuations are subtle, they suggest that mass distribution beneath the crust is actively changing. This could indicate magma migration, the collapse of subterranean structures, or even shifts in the density of the mantle itself. Such changes in gravity have historically been linked to large-scale geophysical events, including major earthquakes and volcanic activity. If this trend continues, it could signal the build-up to something far more dramatic than just an ongoing swarm of tremors. At the same time, researchers monitoring Earth's electromagnetic field have observed irregularities that seem to correspond with the seismic activity. The planet's magnetic field is primarily generated by the movement of molten iron in the outer core, but disturbances in the crust, such as deep underground fractures, can temporarily alter localized magnetic fields. Some areas with increased tremor activity have shown a weakening in magnetism, while others have experienced brief but intense magnetic fluctuations. These changes suggest that deep geological forces may be influencing not just the surface, but the planet's fundamental electromagnetic stability. If such disturbances persist, they could have implications for everything from electrical grid stability to satellite operations. Adding another layer of intrigue, scientists have detected unexplained pulses of energy radiating from deep within the Earth. These ultra-low frequency waves, undetectable by human senses, have been recorded on seismometers and radio observatories worldwide. Some experts suspect that they may originate from stress-induced shifts in the lithosphere, the rigid outer shell of the Earth, while others propose they could be tied to previously unknown interactions between the mantle and the core. Whatever the source, these pulses appear to be increasing in both frequency and intensity, coinciding with the dramatic surge in seismic events. The ocean floors are also undergoing unprecedented changes. Underwater seismographs have registered a rise in microseismic activity along mid-ocean ridges, the vast mountain chains beneath the sea where new crust is formed. Some regions have shown a marked increase in hydrothermal vent activity, spewing superheated water rich in minerals at an accelerated rate. This suggests that magma movement is not just occurring beneath continental plates, but deep within the oceanic crust as well. If this is part of a larger geological shift, it could lead to changes in ocean currents, potentially disrupting global climate patterns in unexpected ways. Meanwhile, deep Earth neutrino detectors, normally used to study cosmic particles passing through the planet, have picked up unusual signatures that appear to originate from within the Earth itself. These particles, known as geoneutrinos, are produced by the radioactive decay of elements deep inside the mantle. Fluctuations in their detection rates could indicate changes in the heat flow within the Earth's interior, possibly linked to shifts in magma movement, or even previously undetected geothermal anomalies. The implications of this are still being studied, but some researchers believe that these readings could provide a new way to predict large-scale geological events before they happen. One particularly strange discovery comes from regions with karst landscapes, areas where underground caves and vast networks of limestone tunnels exist. In several locations, researchers have documented instances where subterranean rivers and underground lakes have either disappeared entirely or suddenly surged in volume. These dramatic shifts suggest that the ground beneath us is moving in ways we do not yet fully understand. Some speculate that these could be the result of deep-seated geological shifts, possibly tied to the same forces responsible for the current tremor outbreak. As new data pours in, it is becoming evident that this is not just an isolated seismic event, but part of a much broader and more complex geological process. What remains to be seen is whether this marks the beginning of a new phase of Earth's evolution, one that could bring unexpected consequences for the surface and for humanity as a whole. Above us, beyond the turbulent surface of the Earth, scientists have begun to explore a startling possibility. Could the dramatic increase in seismic activity be linked to forces originating from space? While earthquakes and tremors are typically understood as purely terrestrial events, growing evidence suggests that cosmic influences may play a more significant role in shaping Earth's geophysical activity than previously believed. One of the most intriguing factors being examined is the effect of solar activity on Earth's internal processes. The Sun, a vast nuclear reactor of unimaginable power, regularly unleashes bursts of energy in the form of solar flares and coronal mass ejections, CMEs. When these immense clouds of charged particles slam into Earth's magnetosphere, they create geomagnetic storms capable of disrupting power grids and communication networks. However, recent studies indicate that these solar events may also have an effect on Earth's lithosphere, the rigid outer shell of the planet. Scientists have noted a curious correlation between major solar storms and spikes in seismic activity. During periods of intense solar activity, fluctuations in Earth's magnetic field appear to coincide with increased tremor frequency and earthquake magnitude. Some researchers theorize that the electromagnetic energy from solar storms could induce subtle changes in the planet's crust, increasing stress along fault lines and triggering tremors that might not have otherwise occurred. If this connection proves valid, it would mean that Earth's seismic behavior is partially influenced by the rhythm of the Sun itself. Beyond solar influences, another potential culprit lies even deeper in space: cosmic rays. These high-energy particles, originating from distant supernovae and other cosmic events, constantly bombard Earth. Most are deflected by our planet's magnetic field and atmosphere, but a fraction penetrate deep into the surface. Some geophysicists speculate that cosmic rays could play a role in altering the mechanical properties of Earth's crust. The idea stems from the fact that cosmic rays are capable of ionizing materials they pass through, including rocks and subterranean minerals. Over time, this could subtly weaken the structural integrity of certain geological formations, making them more susceptible to stress fractures and seismic disturbances. Additionally, an increase in cosmic ray intensity, such as during periods of low solar activity when the Sun's protective heliosphere weakens, could lead to a higher frequency of these effects, potentially explaining some of the erratic tremor patterns observed in recent months. Another extraterrestrial influence being considered is the gravitational impact of celestial alignments. While the Moon's tidal effects on Earth's oceans are well understood, there is growing evidence that its gravitational pull also influences subterranean magma movement. Studies have shown that deep within the Earth, magma reservoirs can experience shifts in pressure due to the cyclic gravitational forces exerted by the Moon, particularly during perigee, the point in its orbit when it is closest to Earth. These effects become even more pronounced when combined with the gravitational forces of other celestial bodies, such as Jupiter and Venus, in what astronomers call syzygy events. Some historical earthquake records indicate that major seismic events have coincided with certain planetary alignments, leading some researchers to hypothesize that gravitational interactions could subtly tug at Earth's internal structures, amplifying tectonic stresses and potentially triggering tremors. Adding another layer of complexity to this cosmic puzzle is the potential role of dark matter. This mysterious, invisible substance makes up a significant portion of the universe's mass, yet its properties remain largely unknown. Some physicists have proposed that dark matter could interact with normal matter in ways we have yet to fully comprehend. If streams of dark matter periodically pass through the Earth, as some models suggest, they could deposit energy, or even exert minuscule gravitational forces that might, over time, contribute to the shifting of geological structures. While these ideas remain largely speculative, they open up a tantalizing possibility that the current surge in tremors may not be purely an earthbound phenomenon, but rather part of a broader cosmic interaction. As researchers continue to gather data, new questions emerge. Could Earth's seismic activity be synchronized with larger cosmic cycles? If so, what other celestial forces might be influencing our planet in ways we have yet to recognize? And most importantly, if external cosmic factors can contribute to geological instability, does that mean we are entering an era where planetary disruptions become more frequent and severe? For now, scientists are racing to collect as much data as possible, using deep space observatories, magnetometers, and seismographs to track patterns and correlations. If the answers lie in the cosmos, understanding them may not only unlock new insights into Earth's internal processes but could also redefine our understanding of how planetary systems interact with the vast, unpredictable forces of the universe. Expanding further into the cosmic perspective, another factor being investigated is the potential influence of interstellar objects passing through our solar system. While asteroids and comets are well-documented celestial visitors, recent discoveries have suggested that rogue interstellar bodies, chunks of matter ejected from distant star systems, may be far more common than previously thought. These objects, like the famous Oumuamua and Borisov, traverse space at high velocities and occasionally pass close to Earth's orbit. Though the gravitational influence of a single interstellar object may be negligible on its own, some astrophysicists theorize that cumulative effects from multiple such encounters over millennia could subtly alter Earth's rotational dynamics or even exert minor perturbations on its tectonic balance. Given that Earth's crust is already in a delicate state of equilibrium, Even slight fluctuations in rotational speed or axial tilt could create stresses deep underground, triggering tremors or accelerating existing fault line activity. Another cosmic variable under scrutiny is the potential impact of passing dust clouds and interstellar plasma streams. As our solar system moves through the galaxy, it occasionally drifts through denser regions of cosmic material, vast clouds of ionized particles or microscopic debris left behind by ancient stellar explosions. Some researchers propose that when Earth encounters such regions, increased interaction with charged particles could subtly influence the planet's magnetic field, which in turn might have cascading effects on seismic activity. A particularly fascinating hypothesis revolves around the concept of galactic tides. Just as the Moon's gravitational influence generates ocean tides on Earth, the gravitational pull of the Milky Way itself exerts slow, periodic forces on our planet. Over vast timescales, these galactic tides may subtly stretch and compress Earth's structure, altering the distribution of mass in the mantle and potentially playing a role in long-term seismic cycles. Some astronomers speculate that as our solar system moves through different galactic regions, changes in gravitational exposure could influence deep Earth processes in ways we have yet to fully comprehend. One particularly compelling line of inquiry suggests that Earth may be responding to an influx of exotic particles from beyond our solar system. As high-energy neutrinos, gamma rays, and hypothetical dark energy fluctuations interact with our planet, they could be subtly affecting the behavior of minerals and elements deep within the mantle. Some physicists even entertain the possibility that unknown quantum-scale interactions, perhaps triggered by the presence of dense cosmic radiation, could be nudging geological systems into an increased state of activity. At the fringes of theoretical physics, another possibility emerges: that fluctuations in the very fabric of spacetime itself could be linked to seismic activity. Some models of the universe suggest that ripples in spacetime, caused by massive cosmic events such as black hole mergers or distant supernovae, may propagate across the cosmos, creating barely perceptible distortions in planetary structures. Could Earth be experiencing the aftershocks of an ancient cosmic event, only now manifesting as an increase in underground tremors? While these ideas are still in the realm of speculation, they point to an exciting new frontier in geophysics, one that suggests Earth is far from isolated in its geological processes. If cosmic forces truly play a role in shaping planetary activity, then understanding these interactions could lead to breakthroughs not only in earthquake prediction but also in our broader comprehension of planetary evolution. With cutting-edge space observatories and deep Earth monitoring systems now working in tandem, scientists are closer than ever to unraveling the mysteries of how Earth's seismic activity is influenced by the vast and enigmatic forces of the universe. There is another bizarre possibility that has captured the attention of astrophysicists, one that challenges our understanding of both planetary science and deep space mechanics. Some researchers speculate that Earth may be experiencing seismic disturbances due to gravitational anomalies caused by an approaching dark matter wave. Dark matter, the invisible and mysterious substance that makes up approximately 85% of the universe's mass, is still largely theoretical. While we can't see or directly detect it, we know it must exist due to the gravitational effects it exerts on galaxies and cosmic structures. But what if this unseen force wasn't just shaping the movement of stars and planets on a grand scale? What if, for reasons not yet understood, Earth has entered a region of space where dark matter is denser than normal, where undetectable waves of exotic particles are subtly pressing against our planet's core? This idea isn't entirely far-fetched. Some physicists have theorized that dark matter might exist in clumps or filaments rather than being evenly distributed throughout the cosmos. If Earth has drifted into one of these high-density regions, the increased gravitational pull from dark matter could be subtly distorting the planet's internal structure, triggering stress points in the mantle and causing tremors to occur more frequently. Mathematical models suggest that if dark matter interacts, even weakly, with normal matter, it could have strange and unpredictable effects on planetary behavior. One controversial paper proposed that if dark matter has even the slightest interaction with atomic nuclei, it could be responsible for unexplained seismic patterns recorded throughout history. Scientists examining deep Earth data have noted peculiar waves, seismic signals that don't conform to known tectonic movements. These signals, originating from hundreds of kilometers beneath the surface, resemble the effects one would expect from gravitational fluctuations rather than conventional geological processes. Even more unsettling is the possibility that Earth could be experiencing a dark matter storm, a high-velocity stream of invisible particles sweeping through the solar system, temporarily altering planetary dynamics. If such a storm were passing through, its effects might not be immediately obvious. Instead, they could manifest as a slow, subtle increase in stress across Earth's geological layers, ultimately reaching a tipping point where tremors and quakes become more frequent and intense. While mainstream science is still grappling with how dark matter could influence planetary physics, others are exploring the even stranger idea of cosmic string interactions. Cosmic strings, hypothetical, ultra-thin filaments of high-energy density that may have formed in the early universe, are theorized to stretch across vast distances, potentially spanning entire galaxies. If a cosmic string were to pass through or near our solar system, it could create a momentary gravitational disturbance powerful enough to induce stresses deep within Earth's mantle. In some models, these strings move at nearly the speed of light, cutting through space like celestial knives, warping spacetime in their wake. A passing cosmic string might generate micro-fluctuations in Earth's gravitational field, imperceptible to us on the surface but potentially significant enough to disrupt delicate geological balances deep underground. These disruptions could trigger pressure shifts in magma chambers, increase fault line activity, or even alter the flow of subterranean fluids that help regulate seismic stability. And then there is the even more speculative concept of Earth encountering an exotic particle field, a yet undiscovered form of radiation or subatomic energy that exerts an unseen influence on planetary matter. Some astrophysicists theorize that rare bursts of high-energy exotic particles, originating from deep space phenomena such as quasars or magnetars, could interact with elements inside Earth's crust, subtly weakening the bonds that hold tectonic plates together. If such an effect were occurring now, it might help explain why an unprecedented number of tremors have been detected in such a short span of time. The key to unlocking these mysteries may lie in cross-disciplinary research, combining the efforts of geologists, astrophysicists, and quantum physicists to examine whether cosmic forces could be leaving a tangible imprint on Earth's seismic activity. If the tremors we're experiencing are being driven not just by internal geological shifts, but by forces originating from deep space, then our understanding of planetary science may need to be rewritten entirely. Another compelling angle to explore is the possibility that these tremors are being triggered by fluctuations in the fabric of space-time itself, distortions in reality caused by gravitational waves. Gravitational waves, first confirmed in 2015 by LIGO, Laser Interferometer Gravitational Wave Observatory, are ripples in space-time produced by extreme cosmic events such as black hole mergers or neutron-star collisions. While these waves are usually too weak to affect planetary bodies in any noticeable way, what if Earth has recently encountered an unusually powerful gravitational disturbance? Some astrophysicists speculate that if a colossal black hole merger had occurred relatively close to our solar system in cosmic terms, perhaps within a few hundred light years, the resulting gravitational waves could be far more intense than anything previously recorded. These waves might create microscopic shifts in planetary mass distribution, exerting stress on Earth's crust and subtly altering the equilibrium of its tectonic plates. Unlike traditional earthquakes, which originate from faults and subduction zones, gravitationally induced tremors might be more evenly distributed across the planet, explaining why the recent surge in seismic activity has been so widespread. But there's another possibility that is even more unsettling: the idea that Earth is being affected by an unknown type of gravitational anomaly, one that could be linked to hidden cosmic structures. Some physicists propose that vast, undetectable gravitational currents, shaped by the mass of dark matter or unseen planetary bodies, may crisscross our galaxy. If Earth has entered a region where these forces converge, we could be experiencing a rare and temporary distortion in gravitational balance. One highly speculative theory suggests that the solar system may be passing through what is known as a gravitational eddy, a region of space where competing gravitational forces from nearby celestial objects interact in unpredictable ways. This could be caused by the presence of rogue planets, hidden black holes, or even ancient remnants of cosmic collisions that have left behind lingering disturbances in the gravitational field. Such an event could temporarily amplify seismic forces within Earth, increasing the likelihood of tremors without any direct tectonic cause. There is also the strange and controversial idea that the planet's core itself might be responding to external gravitational shifts in unexpected ways. Some researchers have proposed that deep beneath the Earth's surface, the metallic core may be subtly oscillating due to changes in the gravitational field surrounding our solar system. If the core's movement is slightly disrupted by an outside force, whether it be gravitational waves, cosmic radiation pressure, or even magnetic fluctuations, it could send unpredictable stress waves through the mantle, leading to tremors and seismic instability. Expanding on this concept, there is growing discussion about whether gravitational anomalies caused by passing stellar objects, such as interstellar asteroids, rogue planets, or even small black holes, could exert temporary but measurable effects on Earth's geology. Some simulations suggest that if a dense, fast-moving object of significant mass were to pass within a few dozen astronomical units of our planet, it could momentarily distort our gravitational field, creating tidal forces deep within the planet's structure. One of the biggest questions in all of this is whether these tremors are an isolated incident or the beginning of a larger pattern. If gravitational disruptions are indeed playing a role, could they be pointing to something even more significant? Some astrophysicists believe that if Earth has entered a region of space with higher than normal gravitational flux, we may begin to see other planetary changes as well, such as shifts in Earth's axial tilt, variations in the length of days, or even disruptions in the Moon's orbit. If Earth is indeed experiencing gravitational distortions from an unknown cosmic source, then the implications could be far-reaching. One area of increasing scientific focus is how these gravitational shifts might interact with Earth's magnetic field. The planet's magnetic shield, generated by the movement of molten iron in the outer core, is a crucial defense against solar radiation and cosmic particles. However, if external gravitational forces are subtly warping the core's dynamics, the planet's magnetic field might become temporarily unstable, leading to unusual electromagnetic disturbances. Some satellite readings have already detected unexplained fluctuations in Earth's magnetosphere, small but noticeable changes that suggest an outside force may be exerting influence. Could this be a sign that a nearby massive object, a rogue planet, a dark matter cluster, or even a stellar remnant, is subtly pulling on Earth's internal structure? If so, we could be dealing with a slow-motion cosmic event, one that is affecting not just seismic activity but also Earth's broader geophysical balance. Even more intriguing is the possibility that gravitational distortions are altering the behavior of the ionosphere, the upper layer of Earth's atmosphere that plays a key role in radio wave propagation and space weather interactions. Some researchers suggest that if a gravitational anomaly is strong enough, it could stretch or compress this layer, creating disruptions in GPS signals, radio communications, and even weather patterns. Reports of unusual atmospheric phenomena, such as sudden changes in jet stream behavior or the appearance of strange electromagnetic pulses detected by satellites, might be connected to the same underlying cosmic disturbance. There is also speculation that these gravitational anomalies could be affecting time itself, albeit in minuscule, almost imperceptible ways. According to Einstein's general relativity, strong gravitational fields can warp the fabric of space-time, causing time to flow differently depending on the intensity of the distortion. If a powerful gravitational wave or a hidden mass is subtly affecting Earth, it could be introducing microscopic variations in atomic clocks around the world. Some highly sensitive observatories, including those that monitor pulsar timing arrays, are already searching for inconsistencies that could hint at unknown gravitational interactions. If time distortions were found to be linked to the recent seismic activity, it would represent one of the most extraordinary discoveries in modern science, evidence that planetary dynamics are not just driven by internal geological processes, but also by the hidden forces of the cosmos itself. Further complicating matters is the role of dark matter, the invisible substance that makes up approximately 85% of the universe's mass. While dark matter does not interact with normal matter in the traditional sense, its gravitational effects are undeniable. If a dense pocket of dark matter has drifted through or near our solar system, it could be exerting an imperceptible but significant pull on Earth's structure. Some exotic theories even propose that interactions between dark matter and the planet's core could generate additional heat, subtly influencing magma flow and potentially contributing to the increase in tremors. This raises the question, has anything like this happened before? While no direct records exist of gravitational anomalies triggering earthquakes, some ancient myths and historical accounts describe bizarre celestial phenomena preceding major geological disasters. Could past civilizations have witnessed unexplained cosmic disturbances that modern science is only now beginning to understand? Some researchers have looked into historical records of aurora-like phenomena occurring in unusual latitudes, unexplained disruptions in ocean currents, and even ancient structures that seem aligned with changes in the sky, all of which could hint at past interactions between Earth and unseen cosmic forces. Deep beneath our feet, the Earth's core remains one of the most mysterious and least understood regions of our planet. Though hidden from direct observation, it is the driving force behind many of the geological and magnetic processes that shape the world above. Scientists believe that the core is composed primarily of iron and nickel, with temperatures soaring to over 9,000 degrees Fahrenheit, hotter than the surface of the Sun. However, recent tremor activity has led some to speculate that something unusual may be happening deep within this hidden inferno. One of the most radical theories suggests that the core may not be as stable as once believed. Some researchers argue that shifts in the core's structure, whether through unexpected fluctuations in heat, changes in the distribution of heavy elements, or even external gravitational influences, could be triggering the recent surge in seismic activity. If the core is experiencing a sudden phase transition, where parts of its liquid outer layer are crystallizing at a faster rate, it could lead to irregular convection currents, throwing the entire mantle into disarray. Even more bizarre is the idea that an undiscovered anomaly exists at the very center of the planet, a dense, unknown object that has slowly been altering the core's movement for millennia. Some speculative models propose that a fragment of an ancient neutron star could be buried within the Earth, left over from a cosmic collision billions of years ago. If such an object were present, its intense gravitational field could create subtle yet powerful distortions in the planet's internal dynamics, causing deep tremors that ripple outward through the mantle. Another theory gaining attention is the concept of core oscillations, the idea that the inner core periodically shifts back and forth in rotation, slightly speeding up or slowing down relative to the surface. While this phenomenon has been proposed before, new seismic readings suggest that the inner core might be behaving even more unpredictably than previously thought. Some data indicates that the core could be undergoing a temporary reversal in its rotational pattern, where the solid inner core is slowing down compared to the rest of the planet. If this shift is happening on a large enough scale, it could be affecting the flow of molten rock in the outer core, disrupting the magnetic field and possibly triggering instability throughout the mantle. Some researchers have even proposed a scenario where the inner core might be shifting its position slightly, moving off-center from the rest of the planet. While this might sound extreme, computer models suggest that uneven heat distribution and variations in material composition could cause the core to become unbalanced over long periods. If the core is indeed tilting or shifting slightly, the resulting gravitational inconsistencies could create pressure pockets in the mantle, leading to sudden releases of seismic energy, possibly explaining the increased tremor activity worldwide. Complicating matters further, new magnetic field anomalies have been detected in regions that correlate with increased earthquake activity. This has led some to speculate that the Earth's magnetic field itself may be experiencing distortions caused by deeper core movements. The last known full magnetic reversal, a phenomenon where the north and south poles switch places, occurred around 780,000 years ago. However, some geophysicists believe that we may be witnessing the early stages of another such event. If the core's movement is linked to these changes, it could have unforeseen consequences for the entire planet, from increased radiation exposure to disruptions in animal migration patterns and even shifts in atmospheric circulation. Perhaps even more alarming is the possibility that an entirely new process is unfolding within the Earth, one that has not been recorded in human history. Some models suggest that if heat flow from the core to the mantle has changed dramatically, it could lead to a phenomenon known as mantle detachment. In this scenario, certain sections of the mantle could become unstable, breaking away in slow-moving waves that push against the crust. This could result in unpredictable seismic swarms, deep underground pressure buildups, and an increase in volcanic activity. If such a process were underway, it might explain why tremors are occurring in unexpected locations and why they seem to be happening at an unprecedented frequency. Of course, without direct access to the core itself, much of this remains speculation. Scientists rely on seismic wave analysis, gravitational measurements, and electromagnetic field studies to infer what might be happening deep inside the Earth. Let's take a deeper dive into some of the more speculative and fascinating ideas we've just touched upon, exploring them with a level of detail that will leave you wondering what's truly going on beneath our feet. We'll break down these terms and concepts, connecting them to the tremors that have been shaking the planet. So, hold on to your seat as we unravel the hidden mysteries of Earth's core. 1. Core oscillations, the planet's hidden dance. Core oscillations might sound like something out of a science fiction novel, but it's a phenomenon that some scientists believe could be behind some of the tremors rattling our world. The idea is that Earth's inner core, a dense, solid ball of iron and nickel, might not rotate exactly in sync with the rest of the planet. Imagine the core slowly accelerating or decelerating over time, like a wheel with a slight imbalance that speeds up or slows down. The cause? Heat differences, convection currents, and the interaction of molten materials in the outer core that could change the movement of the inner core. Now, why does this matter? Well, if the inner core is rotating at a different speed than the outer layers of the Earth, it could create gravitational forces that disrupt the flow of molten materials. These fluctuations could lead to destabilized convection currents, which might push magma in unpredictable directions. That could explain some of the strange tremors we're seeing worldwide. The movement of the molten iron could be triggering mini shockwaves through the planet's mantle, leading to sudden seismic activity. It's not just about the core rotating differently, it's about how that rotation affects the entire planet's internal workings. Imagine a situation where this core oscillation becomes more pronounced. The interactions between the inner core and outer core could potentially lead to strange magnetic anomalies, disturbing our planet's magnetic field. If this were happening on a large scale, it could have ripple effects on Earth's tectonic plates, amplifying the tremors we're seeing. 2. Core shifting, the unstable center of the Earth. Now, let's talk about a potentially mind-blowing scenario. What if the Earth's core is actually shifting? It sounds far-fetched, but it's not as impossible as you might think. The Earth's core is essentially floating within the mantle, suspended by the pressure and gravitational forces surrounding it. But what if, over time, that core has started to shift, tilting or moving slightly off-center? This could happen for a variety of reasons. For one, variations in heat distribution could cause parts of the inner core to expand or contract, pulling the entire structure off-center. Imagine if this happened gradually, over millions of years. This slow shift could distort the distribution of pressure throughout the planet. As a result, certain areas of the mantle might become stressed, which could trigger seismic swarms and earthquakes in places we wouldn't normally expect. If the core were to shift significantly, it could cause waves of pressure to ripple through the mantle, resulting in earthquakes and volcanic eruptions. There could be small, localized tremors at first, but the more significant shifts could trigger massive seismic activity. Think of it like a ripple effect, starting at the core and radiating outwards in all directions. The real kicker here? Scientists have already detected irregular seismic readings from locations far removed from any obvious fault lines, which some believe could be related to this kind of deep core movement. If the Earth's center is slowly shifting, it could explain the bizarre patterns of tremors that seem to have no clear origin. 3. Mantle detachment, the crust cracking open. Let's now explore the idea of mantle detachment, a terrifying concept in which parts of the Earth's mantle could become unstable and slowly break away. The mantle is the layer between the Earth's crust and the core, composed of rock that is in a constant state of movement due to heat-driven convection currents. Under normal circumstances, the mantle behaves like a thick, viscous fluid, constantly shifting and flowing, but in some places, things could go horribly wrong. Imagine if certain sections of the mantle became weak. This could happen due to shifts in heat flow or changes in pressure from the core. As the mantle material weakens, it could eventually detach, creating massive pressure pockets that push against the Earth's crust. These pressure buildups could lead to widespread seismic activity, as the mantle releases its energy in the form of tremors. The breaking apart of the mantle would not be a sudden event but could instead unfold gradually, creating a constant series of tremors, each one stronger than the last. What makes this even more disturbing is that this could lead to a chain reaction. As parts of the mantle detach, they could create fissures or fractures deep within the Earth's crust. These fractures might open up new volcanic pathways, making certain regions more prone to volcanic eruptions. As the crust breaks, it could trigger violent earthquakes that could affect entire continents. 4. The magnetic field disturbances, more than just a switch. Now let's take a step back and talk about the Earth's magnetic field, specifically, some of the more unusual magnetic anomalies that have been detected in recent years. The magnetic field is created by the flow of molten iron and nickel in the outer core, and it plays a vital role in shielding us from harmful solar radiation. But what if something in the core's movements is causing distortions in the field? Magnetic field reversals, where the magnetic poles flip, are known to occur over geological timescales. But what if we're witnessing the early stages of a reversal, one that could disrupt the delicate balance of our planet's electromagnetic system? If the inner core's movements are influencing the molten material's behavior in ways we don't fully understand, it could lead to shifts in the magnetic field. These shifts might be subtle at first but could eventually grow stronger, affecting everything from the behavior of migrating animals to our reliance on GPS and communications satellites. In fact, recent data suggests that certain regions of the Earth's magnetic field are weakening, and some scientists are drawing a correlation between this weakening and increased seismic activity. If the magnetic field's behavior is linked to the core's internal dynamics, then disturbances in the field could be an early warning sign of more dramatic changes below the surface. Whether this will lead to a full magnetic reversal or just localized anomalies, the impact could be felt in ways we're not yet prepared for. 5. The neutron star fragment, a wild, yet intriguing idea. We're now venturing into the realm of the truly speculative, a concept so strange that it sounds like it belongs in a science fiction thriller, the idea of a fragment of a neutron star being buried within the Earth's core. Neutron stars are the remnants of massive stars that have exploded in supernovae, and they are among the densest objects in the universe. Their gravitational pull is so strong that a single teaspoon of neutron star material would weigh billions of tons. But what if a piece of a neutron star somehow found its way into Earth's core, billions of years ago, during the planet's formation? This fragment could be influencing the core's behavior in unpredictable ways. Imagine the gravity of this dense fragment affecting the surrounding molten iron and nickel, altering the convection currents in ways we can't fully understand. If the fragment were large enough, it could create subtle disturbances in the Earth's magnetic field, triggering seismic activity as the planet's internal structure adjusts to the presence of this mysterious object. While this idea may seem far-fetched, it's worth noting that some physicists believe it could be possible for fragments of other celestial bodies to end up in Earth's interior during the early stages of the planet's formation. If we could confirm such an anomaly, it would open up a whole new realm of scientific exploration, one that would shed light on the planet's deep, hidden history. Now, let's shift our focus to an often overlooked, but crucial factor that could be influencing the tremors we're seeing worldwide: the oceans. While we typically associate seismic activity with earthquakes shaking land masses, the vast bodies of water covering our planet also play a significant role in the Earth's dynamic processes. When we talk about seismic events, we can't ignore the deep, mysterious waters beneath the ocean's surface. The ocean floor is home to tectonic plates, undersea volcanoes, and fault lines that may be directly or indirectly contributing to the tremor activity we're witnessing. Most of us don't think about earthquakes happening under the ocean. Yet, the ocean floor is riddled with fault lines, many of which are just as active as their land counterparts. These undersea faults are connected to the same tectonic processes that cause earthquakes on land. Tectonic plates beneath the ocean shift, grind, and collide, just like on the surface. When these plates move, they release immense amounts of energy, causing undersea earthquakes that send shockwaves throughout the ocean. These tremors can sometimes be felt on land, especially along coastal regions, but they can also amplify other seismic events occurring deeper within the Earth's crust. The frequency of these underwater quakes is on the rise, and it's not just about the size or the number of quakes. It's also about how these tremors travel. Seismic waves produced under the ocean can reverberate through the Earth's crust, sometimes making their way to distant fault lines, even triggering land-based tremors. The more seismic activity there is beneath the ocean, the more it could potentially influence what's happening on land. These oceanic tremors might not always get the attention they deserve, but they're quietly contributing to the overall seismic picture. And the truth is, with advances in technology, scientists are beginning to detect an increasing number of ocean-based quakes that were previously difficult to monitor. With thousands of miles of oceanic fault lines, there is much more happening beneath the surface than we previously thought. Another crucial player in this equation are the underwater volcanoes scattered across the ocean floor. We're all familiar with the impact of volcanic eruptions on land, but underwater volcanoes are a whole different story. Known as seamounts, these submerged volcanoes rise from the ocean floor and can produce dramatic eruptions, releasing molten lava into the water. The eruptions are capable of generating powerful shock waves that travel through the ocean, creating ripples in the surrounding area. These underwater eruptions can significantly affect the Earth's crust by creating massive pressure waves beneath the ocean that ripple through to the surface. Even though these volcanic events are often hidden beneath miles of water, they exert a tremendous amount of force. What's more, seamounts are often located near tectonic plate boundaries, where most of the world's earthquake activity originates. When an underwater volcano erupts, it can interact with the nearby faults, contributing to a series of tremors both beneath the ocean and on land. The power of underwater eruptions can extend far beyond their location, affecting seismic activity on the other side of the planet. Additionally, the buildup of pressure beneath the ocean's surface has the potential to trigger multiple seismic events, which may result in more tremors and more widespread earthquakes. Let's also not forget the role of oceanic hotspots, areas where magma from deep within the Earth's mantle rises to the surface, causing intense volcanic activity. These hotspots are responsible for some of the most significant volcanic eruptions in history, and while we often think of them as land-based phenomena, many of them are located under the ocean. When magma rises to the surface and interacts with the Earth's crust, it creates a dynamic that causes earthquakes and tremors to occur not only beneath the ocean but also on land. But it's not just the geology beneath the ocean that could be contributing to the tremors we're witnessing. Ocean currents and the movement of water can also influence seismic activity in ways that are just beginning to be understood. The massive weight of the ocean, combined with the movement of tectonic plates beneath the water's surface, can cause shifts in the Earth's crust. These shifts might trigger earthquakes or even more widespread seismic activity. As the Earth's temperature changes, so too does the movement of water, affecting the overall stability of the ocean floor and increasing the potential for seismic disturbances. This interconnectedness between ocean dynamics and tectonic forces is a crucial factor to consider when trying to understand the full scope of the tremor increase. With so many unknowns in the complex interactions between the Earth's core, its oceans, and the dynamic processes at play beneath the surface, we are only beginning to scratch the surface of what's happening underneath our feet. While ocean-based seismic activity may not always make headlines, it plays a vital role in the ongoing global rise in tremors. The more we investigate and monitor these undersea events, the clearer it becomes that the oceans are far from passive players in the Earth's seismic activity. They are intricately linked to the very processes that shape the Earth's surface and could provide valuable insights into the forces that are currently at work below us. Let's dive into some notable events in history that underscore the significant relationship between the ocean and seismic activity. These real-world occurrences offer valuable insights into how the oceans play a pivotal role in triggering tremors, earthquakes, and even tsunamis, making them more than just passive bodies of water. One of the most infamous examples of ocean-induced seismic activity is the 2004 Indian Ocean earthquake and tsunami. On December 26, 2004, a massive undersea earthquake with a magnitude of 9.1 struck off the coast of Sumatra in Indonesia. This earthquake, originating from the tectonic boundary where the Indo-Australian plate meets the Eurasian plate, released an enormous amount of energy. The shift of the ocean floor triggered a tsunami that traveled across the Indian Ocean, causing devastation in several countries, including Indonesia, Sri Lanka, India, and even reaching the eastern coast of Africa. The earthquake was one of the most powerful ever recorded, and it caused one of the deadliest natural disasters in history, claiming over 230,000 lives. The tsunami generated by the seismic event surged at speeds of up to 500 miles per hour in some areas, displacing entire coastal communities. The destruction was far-reaching, demonstrating how undersea earthquakes can have catastrophic consequences not only beneath the ocean but on land as well. This event serves as a potent reminder of how ocean-based seismic activity can generate shockwaves capable of affecting large parts of the globe. In 2011, Japan experienced another catastrophic event linked to the ocean, the Tohoku earthquake and tsunami. On March 11, a magnitude 9.0 earthquake struck off the coast of northeastern Japan, causing a massive undersea shift along the boundary between the Pacific and North American plates. This seismic event was one of the strongest in recorded history, and its aftermath was nothing short of devastating. The earthquake was followed by a powerful tsunami that inundated Japan's coastal regions, causing widespread destruction and leading to the Fukushima nuclear disaster. What made this event so significant is the deep connection between seismic activity, the ocean, and the land. The tectonic movement along the oceanic trench unleashed a seismic wave that affected not only the surrounding area but also triggered a catastrophic tsunami. This disaster emphasized how the ocean floor, particularly tectonic zones, plays an active role in seismic events. The aftershocks from the earthquake reverberated across the Pacific, demonstrating the far-reaching impact of ocean-based tremors. Even further back in history, the 1960 Valdivia earthquake in Chile remains the strongest earthquake ever recorded. On May 22, 1960, a magnitude 9.5 earthquake struck off the coast of southern Chile. The event was triggered by the subduction of the Nazca Plate beneath the South American Plate along the Peru-Chile Trench, an oceanic subduction zone. The earthquake generated a series of tsunamis that struck the coastlines of Chile, Hawaii, Japan, and even the Philippines, with waves traveling across the Pacific Ocean. The sheer scale of the earthquake and its tsunami impact demonstrates just how interconnected seismic events beneath the ocean are with the Earth's larger tectonic systems. The 1960 event caused widespread damage across multiple countries, further underscoring the profound relationship between undersea geological activity and its global consequences. The tsunami waves were so powerful that they impacted remote coastlines thousands of miles away from their origin, spreading seismic energy far beyond the immediate earthquake epicenter. These historical examples illustrate the dynamic and interconnected relationship between oceanic seismic activity and the Earth's tectonic processes. They show us how undersea earthquakes, driven by the movement of tectonic plates and the forces acting beneath the ocean, can trigger massive, far-reaching effects, such as tsunamis, that wreak havoc on both coastal and distant regions. With each of these events, scientists have gathered valuable data about the relationship between oceanic quakes and their ability to affect both the ocean and land, influencing the frequency and magnitude of tremors worldwide. But these examples are not just historical footnotes. They offer a template for understanding how such seismic activity might evolve in the present and future. As we continue to monitor the oceans and the shifting tectonic plates beneath them, we're discovering that these underwater earthquakes and volcanic events may be increasing in frequency and intensity. The recent uptick in tremors recorded around the globe may, in fact, be part of a larger, more complex pattern emerging from the depths of the ocean and extending up through the Earth's crust. In light of this, many scientists are beginning to focus more on ocean-based seismic activity, expanding research efforts into undersea fault lines, subduction zones, and volcanic hotspots. Through advances in seismology and oceanography, we're able to track and better understand the shifting dynamics beneath the ocean's surface. With more sophisticated monitoring systems being placed along the oceanic fault lines, scientists are continuously refining their ability to predict seismic events and their potential impact on the land. So, the next time we hear about a tremor or an earthquake, we might not just be looking at activity on land. Instead, we may be witnessing the far-reaching ripples from the unseen, but immensely powerful, forces at work beneath the ocean. Let's dive deeper into the potential of the oceans to act as an unpredictable force when it comes to seismic events. The ocean is not only a powerful generator of natural disasters, but it can also act as an indicator, a sort of barometer for Earth's seismic health. There are theories being developed that link fluctuating oceanic temperatures and unusual tidal patterns to heightened seismic activity beneath the ocean's surface. Take, for example, the concept of hydrodynamic stress, a term used by scientists to describe the way ocean water, as a massive moving fluid, can impact the Earth's crust. It's been theorized that large shifts in the ocean's mass, like the shifting of tectonic plates beneath the sea, can create pressures that reverberate through the Earth's crust in unusual ways. Changes in ocean currents or unusual heat distribution across the seas could be slowly shifting fault lines, making them more likely to slip. Some researchers have pointed to places like the Mariana Trench, where the deepest parts of the ocean meet tectonic plate boundaries, as areas of extreme concern for potential seismic surges. Interestingly, this link between ocean changes and seismic activity has been observed more frequently during extreme weather events. In particular, major El Niño and La Niña events have been linked to increased seismic activity around the world. During El Niño years, when ocean temperatures are higher than normal, the increase in heat content can cause minor shifts in the ocean's currents. These shifts, though not always noticeable to the human eye, are believed to have a cascading effect on tectonic plates. They may not cause immediate massive earthquakes, but over time, they could alter the pressure on subduction zones or fault lines, leading to larger seismic events. Oceanographers and geologists have been collaborating on this theory for years, but the challenge lies in quantifying and isolating the impact of ocean currents from other forces acting on the Earth's crust. If they are able to make more breakthroughs in this research, it could potentially change how we understand the relationship between the ocean's behavior and the forces that shake the Earth. Additionally, scientists are looking at the role of oceanic trenches in seismic activity. These deep underwater valleys are formed by the subduction of one tectonic plate beneath another, often leading to highly volatile areas with intense seismic activity. In fact, it's believed that a large portion of the Earth's most powerful earthquakes originate from these subduction zones. But what's fascinating is how these regions, particularly along the Pacific Ring of Fire, are sometimes subject to seismic acceleration when underwater volcanic activity and tremors increase. This acceleration can lead to swarms of earthquakes, as seen in the Cascadia subduction zone off the coast of the Pacific Northwest in the United States. Some researchers speculate that pressure in these zones is building, potentially resulting in a major quake in the near future. The thought of underwater volcanic activity is another significant factor in our understanding of oceanic seismic events. Submarine volcanoes are scattered across the world's oceans, often lying in remote regions far from human populations. These volcanoes are capable of triggering catastrophic events, both underwater and above the surface. When an underwater volcano erupts, it can displace a massive amount of water, creating an enormous shockwave. This shockwave, in turn, can trigger tsunamis and earthquakes. But what's even more fascinating is that there is evidence suggesting that some of these eruptions may be linked to long-term seismic patterns that we don't fully understand. Submarine eruptions can release gases, minerals, and other chemicals into the water, altering ocean chemistry in subtle ways. Changes in ocean salinity, acidity, and temperature could, in turn, have an impact on the stability of tectonic plates. While scientists are still working to establish concrete evidence of this connection, the possibility is certainly intriguing. Researchers have even begun to suggest that changes in ocean salinity and temperature gradients could be tied to the occurrence of large-scale tremors. For example, sudden shifts in ocean temperature, such as those caused by climate change, can lead to changes in pressure along the ocean floor. These changes might be enough to trigger a release of tension in certain fault lines, leading to an earthquake. This is particularly evident in deep-sea regions where subduction occurs, and changes in water temperature could affect the buoyancy and movement of tectonic plates. It's not entirely clear yet, but this could provide another piece of the puzzle in understanding how the ocean's dynamic systems interact with the Earth's geological structures. Another area of focus is the impact of the ocean's tides. Tidal forces are generated by the gravitational pull of the Moon and the Sun, and they affect the Earth's crust in a very real, though subtle, way. Every day, the Earth experiences 2 high tides and 2 low tides as the Moon's gravity pulls on the oceans. However, there's growing evidence that these tidal forces may also play a role in triggering seismic events, particularly in certain fault zones. Some seismic events seem to correlate with tidal movements, where higher tides seem to increase the likelihood of tremors. Though this connection is still under investigation, the idea that the Moon's pull on the Earth's oceans could also be pulling the Earth's crust in such a way that it leads to earthquakes is a fascinating concept that's been discussed by many geologists. Looking ahead, one of the most exciting areas of research is monitoring the deep ocean floor for seismic precursors. By using new types of seafloor sensors and advanced imaging techniques, scientists are developing ways to detect the first signs of seismic shifts before they occur. These methods might give us precious minutes, or even hours to prepare for an impending tsunami or earthquake. Scientists are even exploring the potential for underwater drones or robotic technology that could track seismic waves and underwater volcanic activity in real time, allowing for faster responses to emerging disasters. As we continue to delve deeper into the connection between seismic activity and the oceans, it's important to consider how these forces might not just be localized but could also have global consequences. We've already discussed how shifts in ocean temperature and salinity could have an impact on tectonic activity, but another area of significant interest is the role of deep-sea circulation patterns in triggering seismic events. Deep-sea circulation is a critical component of the Earth's climate system, responsible for transporting heat and nutrients around the globe. These circulation patterns are driven by differences in water density, which are determined by temperature and salinity. When these factors shift, whether due to climate change, underwater volcanic activity, or other factors, they can disrupt the balance of forces within the ocean. As deep-sea circulation slows or shifts, it can alter the pressure placed on the ocean floor and, by extension, the tectonic plates beneath it. The resulting pressure changes may trigger small tremors or even large earthquakes. One potential example of this occurred in 2011, when a massive earthquake struck off the coast of Japan, triggering a tsunami that devastated much of the country. While the main cause of this earthquake was the movement of tectonic plates along the subduction zone, there were studies suggesting that changes in ocean circulation patterns could have contributed to the buildup of stress along the fault line. The connection between ocean currents and tectonic plate movement in this instance is still being researched, but the possibility of a direct link is something that scientists are increasingly exploring. To further illustrate the complex interaction between the ocean and seismic activity, we should consider the concept of hydrothermal vents. These underwater geysers are located deep beneath the ocean's surface, where heat from the Earth's core escapes into the water. These vents are not only home to unique ecosystems, but are also thought to play a significant role in the Earth's geological processes. As these vents expel mineral-rich fluids into the surrounding water, they alter the pressure and chemical composition of the surrounding water. This localized change in pressure could, in theory, influence nearby fault lines, contributing to seismic activity. Some scientists have even proposed that the discovery of new hydrothermal vent fields could provide valuable insight into future seismic events. These fields are often located near tectonic plate boundaries, where the Earth's crust is under considerable stress. When new vents are discovered in these regions, it could indicate that the tectonic plates are moving in such a way that could lead to future earthquakes. Although this theory is still in its early stages, it presents an intriguing potential for understanding how the Earth's internal processes are interconnected. In addition to these geological factors, another important area of study is the effect of underwater landslides. While landslides on land are well documented, underwater landslides are far more difficult to study, mainly due to the immense pressure and difficulty in accessing deep ocean areas. However, recent advancements in remote sensing technology have allowed scientists to better understand how landslides on the ocean floor can influence seismic events. Underwater landslides are typically triggered by large-scale shifts in the Earth's crust, such as earthquakes or volcanic eruptions. However, other factors, such as shifts in ocean currents or the rapid accumulation of sediment, can also contribute to underwater instability. When these landslides occur, they have the potential to release massive amounts of energy, sometimes creating seismic waves that reverberate across the ocean floor. In some cases, these seismic waves can trigger subsequent earthquakes or tsunamis, amplifying the effects of the initial event. Perhaps the most significant example of an underwater landslide leading to seismic activity occurred in 1929 off the coast of Newfoundland, Canada. A massive underwater landslide triggered by a powerful earthquake created a chain reaction of seismic events that ultimately led to a devastating tsunami. This event demonstrated just how interconnected the oceans and the Earth's crust truly are, and how a single disturbance in the ocean can have far-reaching effects on seismic activity. As we continue to explore the oceans and their relationship to seismic events, it's becoming increasingly clear that we're dealing with a highly dynamic and interconnected system. The Earth's oceans are not merely a passive component of the planet's environment. They actively shape the forces beneath our feet, influencing everything from volcanic activity to tectonic plate movement. In the coming years, researchers are likely to make new breakthroughs in our understanding of how these forces interact. With advancements in ocean exploration technology, the future of seismic research could provide us with more precise tools to predict when and where these powerful events will strike. For example, by using a combination of underwater sensors, satellite data, and AI-driven analysis, scientists might be able to forecast seismic activity with much greater accuracy. Let's dive deeper into volcanic activity, specifically focusing on how it relates to the seismic tremors and what's happening underground. Volcanic eruptions have always been a subject of fascination due to their immense power and their ability to reshape landscapes almost instantly. But the processes that lead to these eruptions, as well as the seismic activity associated with them, are complex and often not fully understood, even by scientists. When we talk about volcanic activity, the first thing we must understand is that it's a direct result of tectonic plate movements beneath the Earth's surface. As we know, Earth's crust is made up of large slabs of rock, called tectonic plates, that float on the semi-fluid layer of the mantle beneath them. These plates are constantly in motion, albeit slowly, at rates of only a few centimeters per year. However, over time, these movements can create vast changes in the landscape, including the formation of volcanoes. At the heart of many volcanic eruptions is the movement of magma, molten rock that forms deep within the Earth's mantle. Magma is generated when heat and pressure cause solid rock to melt, and this magma rises toward the surface because it's less dense than the solid rock around it. The movement of magma beneath the surface is what often triggers seismic activity. As magma pushes its way toward the surface, it creates pressure on the surrounding rock, leading to small earthquakes or tremors. These tremors are usually signs that magma is on the move, and they can precede a major eruption. The 2010 eruption of Eyjafjallajökull in Iceland is a perfect example of how seismic activity can signal an impending volcanic eruption. Prior to the eruption, there were thousands of small tremors detected in the region, indicating that magma was moving beneath the surface. As the magma reached the surface, it resulted in a massive volcanic eruption, sending ash clouds high into the atmosphere and disrupting air travel across Europe. These tremors are an essential warning sign for volcanologists, allowing them to monitor and predict potential eruptions, though it's never an exact science. Volcanic eruptions can range in size and intensity, from relatively minor events that produce only localized lava flows to catastrophic supervolcano eruptions that can have global consequences. One of the most powerful eruptions in recorded history was the eruption of Mount Tambora in Indonesia in 1815. This eruption is considered the largest in modern history, and its seismic activity was enormous. In the months leading up to the eruption, there were numerous tremors, as magma moved beneath the surface, building up pressure. When the eruption finally occurred, it released an estimated 160 cubic kilometers of magma and ash into the atmosphere. This eruption had global repercussions, causing the year without a summer in 1816, which resulted in widespread crop failures and famine across the northern hemisphere. Even smaller eruptions can have significant local effects. For example, the eruption of Mount St. Helens in the United States in 1980 was preceded by months of seismic activity, with hundreds of small tremors recorded in the region. These tremors were the result of magma rising toward the surface, and they signaled that an eruption was imminent. The eruption itself was devastating, with a massive landslide and explosive release of ash and gas that destroyed entire forests and caused significant loss of life. In some cases, volcanic eruptions can also trigger other natural disasters, such as tsunamis. One example is the eruption of Krakatoa in 1883. This eruption was so violent that it caused the surrounding sea to surge, triggering massive tsunamis that devastated coastal areas around the Sunda Strait. The eruption was preceded by weeks of seismic tremors, and its aftermath was felt worldwide, with ash clouds causing temperature drops and disruptions to global weather patterns. The process that leads to volcanic eruptions is known as volcanism, and it can occur in different types of tectonic settings. The most common type of volcanism occurs at divergent plate boundaries, where two tectonic plates are moving away from each other. This creates gaps in the Earth's crust, allowing magma to rise and form volcanoes. A prime example of this type of volcanism is the Icelandic volcanic system, where the North American and Eurasian plates are pulling apart. This has led to the formation of many of Iceland's active volcanoes, including the infamous Age of Geological. On the other hand, most of the world's most dangerous volcanoes are located at convergent plate boundaries, where two plates are colliding. When one plate is forced beneath another, it creates a subduction zone, and the melting of the descending plate forms magma. This magma rises to the surface and creates explosive volcanoes. The Pacific Ring of Fire is home to many of the world's most active and dangerous volcanoes, including Mount Fuji in Japan, Mount Vesuvius in Italy, and Mount Pinatubo in the Philippines. In addition to seismic tremors, volcanic eruptions are also influenced by the type of magma involved. There are three main types of magma: basaltic, andesitic, and rhyolitic. Basaltic magma is low in viscosity, meaning it flows easily and results in relatively gentle eruptions, like the ones seen in Hawaii. Andesitic and rhyolitic magmas are more viscous, meaning they resist flow and can lead to more explosive eruptions. The eruption of Mount St. Helens, for example, involved andesitic magma, which is why it produced such a violent explosion. The eruption of a volcano is often followed by secondary effects, such as pyroclastic flows, which are fast-moving clouds of hot gas, ash, and rock that can travel at speeds of up to 700 kilometers per hour. These flows are incredibly dangerous and can cause widespread destruction in a matter of minutes. Another secondary effect is the creation of lahars, which are mud flows created when volcanic ash mixes with rainwater. Lahars can flow down river valleys, destroying anything in their path, including towns and infrastructure. While volcanic eruptions are dramatic, they also play a key role in shaping the Earth's landscape. Over time, the lava flows from eruptions build up and create new landforms, such as volcanic islands. The Hawaiian Islands, for example, were formed by the eruption of countless volcanoes over millions of years. The volcanic activity continues today, with the island of Kilauea being one of the most active volcanoes in the world. Volcanoes also have an impact on the atmosphere. Large eruptions release massive amounts of gases, such as carbon dioxide, sulfur dioxide, and ash into the atmosphere. These gases can have long-lasting effects on global climate. For example, the eruption of Mount Pinatubo in 1991 released so much sulfur dioxide into the atmosphere that it caused a temporary cooling effect, lowering global temperatures by about 0.5 degrees Celsius for the following year. This cooling effect is known as volcanic winter. When we look deeper into the underlying mechanics of volcanic activity, it's important to understand the role of the Earth's crust and the forces at play within it. As mentioned, Earth's lithosphere, the rigid outer layer, is broken into several tectonic plates. These plates are in constant motion, driven by convection currents in the mantle. As these plates interact with one another, stress builds up along fault lines, which can lead to seismic activity, often in the form of earthquakes and tremors. But when it comes to volcanoes, the interplay between these tectonic plates creates the conditions necessary for magma to rise to the surface. Subduction zones, where one plate is forced beneath another, are often the sites of the most explosive volcanic eruptions. The Pacific Ring of Fire is a prime example of this type of tectonic activity, where the subduction of oceanic plates beneath continental plates results in the creation of powerful and often unpredictable volcanoes. Another important factor in volcanic eruptions is the composition of the magma involved. While we often talk about magma in general terms, it's crucial to understand that not all magma is created equal. The chemical composition of magma directly affects how it behaves when it rises toward the surface. Basaltic magma, for example, is low in silica, which makes it relatively fluid. This type of magma results in effusive eruptions, meaning it flows out of the volcano gently and forms large, broad volcanic shields. The eruptions in Hawaii are a perfect example of this. The volcanoes there, such as Kilauea, produce lava flows that can travel for miles, but the eruptions themselves are less explosive and more predictable. These types of eruptions are generally less hazardous, but they still reshape the land around them and create entirely new ecosystems. In contrast, andesitic and rhyolitic magmas are much more viscous because they contain higher levels of silica. These types of magma do not flow as easily and are more prone to trapping gas within them. When gas pressure builds up beneath the surface, it can lead to highly explosive eruptions. One of the most famous examples of this type of eruption is the eruption of Mount Vesuvius in AD 79, which destroyed the Roman cities of Pompeii and Herculaneum. The eruption was so explosive that it released a cloud of ash and pumice that rose 33 kilometers into the atmosphere, raining down volcanic debris and pyroclastic flows on the surrounding areas. Pyroclastic flows are one of the deadliest aspects of explosive volcanoes. These flows consist of hot gases, ash, and fragments of rock, which can travel at speeds of up to 700 kilometers per hour, moving down the sides of volcanoes like a fast-moving avalanche. Because of their speed and temperature, they are almost impossible to outrun, and they can obliterate everything in their path. The eruption of Mount Pelee in Martinique in 1902, for example, generated pyroclastic flows that destroyed the entire city of Saint-Pierre, killing nearly 30,000 people in a matter of minutes. Volcanic eruptions don't just affect the areas immediately surrounding the volcano itself. They also have far-reaching effects on the atmosphere and climate. When large amounts of sulfur dioxide are released into the atmosphere during an eruption, they combine with water vapor to form sulfuric acid droplets, which can have a cooling effect on the planet. This phenomenon is known as volcanic winter, and it can cause significant changes in the climate, as it blocks sunlight and lowers global temperatures. One notable instance of volcanic winter occurred after the eruption of Mount Tambora in Indonesia in 1815. This eruption, one of the largest in recorded history, released an enormous amount of volcanic ash and gases into the atmosphere. The following year, 1816, became known as the year without a summer. Global temperatures dropped significantly, leading to crop failures and widespread famine across the northern hemisphere. The eruption's impact on climate patterns also led to a series of extreme weather events, including unusually cold temperatures and heavy snow in regions far from the volcano itself. In addition to the global cooling effect, volcanic eruptions can also release large amounts of carbon dioxide (CO2), a greenhouse gas. While CO2 is primarily associated with human activities, such as burning fossil fuels, volcanoes also contribute to the planet's carbon cycle. The amount of CO2 released by volcanoes is significantly less than the amount emitted by human activities, but the release of gases during major eruptions can still have a noticeable effect on the environment. In recent years, there has been growing interest in the concept of volcanic monitoring and how we can predict volcanic activity before it results in a catastrophic eruption. Many volcanoes, especially the more active ones, are constantly monitored using a variety of techniques. Seismometers are one of the primary tools used to detect tremors and small earthquakes that often precede eruptions. By analyzing these seismic waves, scientists can determine if magma is moving beneath the surface. The frequency and intensity of tremors can give volcanologists a clue about whether an eruption is imminent or not. Gas monitoring is another critical component of volcanic surveillance. As magma rises toward the surface, it releases gases such as sulfur dioxide, carbon dioxide, and water vapor. By measuring the concentration of these gases, scientists can gauge the amount of pressure building up beneath the surface and estimate how likely it is that an eruption will occur. For example, the release of sulfur dioxide is often associated with an increase in volcanic activity, and significant increases in gas emissions can act as a warning sign. Other methods include ground deformation monitoring, which uses instruments like GPS and radar to track changes in the shape of the ground around a volcano. When magma moves upward, it can cause the ground to swell, forming bulges or cracks. These deformations are often accompanied by seismic activity and gas emissions, providing more evidence that a volcano is preparing to erupt. Despite all these advances in monitoring and prediction, however, volcanic eruptions remain unpredictable. Even with all the data and technology available, it's still difficult to know exactly when or where an eruption will occur. For example, in 1980, Mount St. Helens in Washington state experienced a major eruption that was preceded by months of seismic activity and ground deformation. However, scientists did not anticipate the catastrophic explosion that took place, and it caused significant damage and loss of life. Some volcanoes, like Mount Fuji in Japan, are considered dormant, with no eruptions in recorded history. However, they are still monitored closely because they are located near heavily populated areas. The possibility of a major eruption in densely populated regions is a concern, and scientists are working to develop more sophisticated methods for predicting when these volcanoes might awaken. Finally, it's important to note that while the eruption of volcanoes is often seen as a destructive event, they also play an essential role in the creation of new land. When magma cools and solidifies, it forms new rock formations, and over time, this can result in the creation of new islands, mountains, and even continents. For example, the Hawaiian Islands were formed by a series of volcanic eruptions that took place over millions of years, creating an archipelago that stretches across the Pacific Ocean. In this way, volcanoes continue to shape the Earth's surface, adding to the ever-changing landscape of our planet. Continuing on with the theme of seismic activity and the ongoing changes beneath Earth's surface, the phenomenon of continental drift plays a critical role in shaping the planet's structure. While the focus of this discussion has largely been on volcanic activity, it's impossible to ignore the role of the tectonic plates and the constant shifting of continents that is occurring right beneath our feet. The shifts in Earth's crust are responsible for much of the seismic activity recorded around the globe, including the tremors and quakes that have been reported at an alarming rate recently. Continental drift refers to the movement of the Earth's continents relative to each other, and it's a concept that is directly linked to the dynamics of plate tectonics. The idea was first proposed by Alfred Wegener in the early 20th century. He suggested that the continents were once part of a giant landmass, which he named Pangaea, that gradually split apart and drifted to their current positions over millions of years. At the time, his theory was controversial, but today, we understand that the Earth's lithosphere is divided into large, rigid plates that float on the semi-fluid asthenosphere beneath them. These plates are constantly in motion, moving at a rate of a few centimeters per year. The plates are constantly interacting, either colliding, pulling apart, or sliding past one another. The convergent boundaries, where two plates collide, are often associated with the most dramatic geological events, such as earthquakes, volcanic eruptions, and the formation of mountain ranges. When two continental plates collide, they can create massive mountain ranges, such as the Himalayas, where the Indian plate is colliding with the Eurasian plate. The Himalayas continue to rise as the plates push against each other, and the seismic activity in this region is significant, including tremors that have been recorded recently. One of the most significant consequences of continental drift is the development of rift zones, where tectonic plates pull away from one another. The East African Rift is a prime example of this, where the African plate is pulling away from the Arabian plate. This rift has been slowly splitting the continent of Africa, with the creation of new valleys, lakes, and even the possibility of a future ocean. These rift zones are incredibly dynamic and often result in frequent seismic activity as the crust fractures and new fissures open up. Interestingly, rift zones are not just limited to the land masses. Underwater rift zones, such as the Mid-Atlantic Ridge, where the American, European, and African plates are separating, are just as active. These underwater ridges are home to frequent seismic events and volcanic eruptions that can create new seafloor in real time, adding new land to the planet's oceanic crust. The Mid-Atlantic Ridge spans thousands of kilometers and is constantly reshaping the ocean floor, contributing to the seismic tremors recorded in the surrounding regions. In addition to rifting and collisions, the sliding of plates past each other at transform boundaries can also result in significant seismic activity. The most famous example of this is the San Andreas Fault in California, where the Pacific Plate and the North American Plate slide past each other. This fault has been responsible for some of the largest earthquakes in U.S. history, and recent tremors in the region have been a source of concern for scientists. When these plates grind past one another, stress builds up along the fault line until it is released in the form of an earthquake. These types of earthquakes can cause extensive damage, especially when they occur near densely populated areas. But what does all of this tectonic activity mean in relation to the title of this script? Over 15,000 tremors recorded in 1 month. What's happening underground? Well, the ongoing shifts in the Earth's crust, including the movements of tectonic plates, play a crucial role in the frequent tremors being recorded. While some of these tremors may be small, undetectable by humans, others can have significant impacts on the regions where they occur. As the continents shift and move, they create stress within the Earth's crust, and this stress is often released in the form of tremors or minor earthquakes. These tremors can, in turn, trigger larger seismic events, such as full-fledged earthquakes. What's especially interesting about the recent surge in tremors is that scientists are beginning to recognize patterns in these shifts. The frequency of small tremors has been rising, particularly in regions that are not traditionally known for frequent seismic activity. For example, in areas where continental plates are slowly grinding past one another, like the San Andreas Fault, we're seeing an uptick in minor tremors. Similarly, regions near rift zones, where continents are splitting apart, are also experiencing increased seismic activity, as the plates move further apart and create fractures in the Earth's crust. In fact, some researchers speculate that these tremors could be a precursor to larger, more powerful earthquakes. The release of stress along faults and rift zones is often a gradual process, with smaller tremors leading up to a larger seismic event. By tracking and monitoring these small tremors, scientists can potentially predict when a more significant earthquake might occur, though accurate prediction remains a challenge. The sheer number of tremors occurring in the past month suggests that there may be some underlying shifts happening beneath the surface, but it's not entirely clear what is causing this surge in seismic activity. Some geologists are also investigating the role of mantle plumes in this increase in tremor activity. These upwellings of hot material from the Earth's mantle can cause shifts in the crust, leading to the formation of new rift zones and the opening of cracks in the Earth's surface. As mantle plumes rise toward the surface, they can cause the crust to stretch and fracture, leading to the creation of new seismic activity. The Hawaiian Islands, for example, were created by a mantle plume, and some researchers are wondering if similar plumes could be causing increased seismic activity elsewhere on the planet. Meanwhile, shifting oceanic plates are also contributing to the overall tectonic activity. The motion of the ocean floor is linked to the movements of the continents, and as oceanic plates slowly move and shift, they exert pressure on the surrounding land masses. For instance, the Nazca Plate is slowly moving eastward, pushing against the South American plate. This interaction has resulted in the formation of the Andes Mountains and continues to cause seismic activity along the western coast of South America. These shifts are often accompanied by small to moderate tremors, which could explain some of the recent uptick in seismic activity recorded worldwide. By tracking these movements, scientists can gain valuable insights into the ongoing changes happening beneath the Earth's surface, even if they don't yet fully understand the reasons behind the increased frequency of tremors. The Earth's crust is constantly in motion, and while many of these shifts are slow and gradual, the consequences of these movements can be dramatic, resulting in the tremors, earthquakes, and volcanic activity that shape the landscape of our planet. As we continue to monitor these seismic events, it becomes clear that the Earth is a dynamic, ever-changing planet. Whether the recent uptick in tremors is a sign of a larger geological shift or simply part of the normal ebb and flow of tectonic activity remains to be seen. However, one thing is certain: the movement of continents, the shifting of tectonic plates, and the ongoing seismic activity are all deeply intertwined, influencing the state of our planet in ways we are just beginning to understand. As we continue to delve deeper into the fascinating world beneath our feet, it becomes apparent that the activity we're seeing with earthquakes and tremors is not an isolated incident. The more we understand the tectonic plates, the more we realize how interconnected they are with our planet's history and future. The movement of the plates affects everything from the formation of mountain ranges to the creation of ocean basins and even the triggering of volcanic eruptions. Take, for instance, the event that occurred off the coast of Sumatra in 2004, a catastrophic reminder of just how connected the Earth's plates are. On December 26th, a massive underwater earthquake with a magnitude of 9.1 to 9.3 occurred beneath the Indian Ocean. This event, known as the 2004 Indian Ocean earthquake and tsunami, was one of the deadliest natural disasters in recorded history, killing over 230,000 people across several countries. The earthquake occurred along the Sunda Trench, a subduction zone where the Indian Plate is being forced under the Sunda Plate. This collision and subsequent seismic event released an immense amount of energy that triggered a tsunami with waves as high as 30 meters, wreaking havoc on coastal communities. What's especially interesting about this earthquake is how it illustrates the link between seismic activity and the movement of tectonic plates. The Indian Plate had been slowly pushing into the Eurasian Plate for millions of years, but it wasn't until this fault line ruptured that the full extent of the energy stored along this boundary was released in such a devastating way. It also serves as a reminder that areas along subduction zones, like the Ring of Fire, which encircles the Pacific Ocean, are particularly vulnerable to massive tremors and even catastrophic tsunamis. In addition to these massive seismic events, the subtle, more frequent tremors we're seeing in areas like the San Andreas Fault in California, or even in places not traditionally known for earthquakes, are also contributing to the seismic activity we're discussing. The San Andreas Fault, which stretches over 800 miles through California, is a prime example of a transformed boundary, where two plates slide past each other horizontally. Tectonic stress has been building along this fault line for centuries, and while large earthquakes have been relatively rare in recent decades, minor tremors have increased. Some scientists suggest that the rise in tremors could be signaling the buildup of pressure for a much larger earthquake, and places like Los Angeles or San Francisco are constantly on alert due to the potential risks. Tremors in this area are so frequent that they are often called foreshocks, small earthquakes that occur before a larger one hits. It's important to note that these tremors, though they seem unremarkable in comparison to a major earthquake, serve as a warning sign that the Earth's crust is active and constantly changing. The tectonic plates are moving at an incredibly slow rate, but the consequences of this movement can be felt globally. As these plates shift, They can also cause subterranean fractures, opening up faults deep below the Earth's surface that trigger subsequent seismic activity. In some instances, like the 1994 Northridge earthquake in California, these fractures result in significant ground shaking, leaving communities reeling from the aftermath. While the Northridge earthquake wasn't as devastating as others, it was a wake-up call for residents in earthquake-prone areas, emphasizing the unpredictable nature of seismic activity. Another example of this kind of tectonic activity is in Iceland, which sits directly on top of the Mid-Atlantic Ridge, the boundary between the North American and Eurasian plates. Iceland is an active volcanic hotspot, with frequent eruptions and earthquakes. One of the most notable recent events in Iceland was the eruption of Eyjafjallajökull in 2010, which disrupted air travel across Europe for days. The eruption was caused by the movement of tectonic plates along the Mid-Atlantic Ridge, releasing pressure and magma from beneath the surface. The event also caused minor tremors, which, while not causing major destruction, served as a reminder of the continuous activity beneath the island. But the tectonic activity we're seeing globally doesn't just affect the surface of the Earth. It also has ripple effects on the atmosphere. Volcanic eruptions, especially massive ones, can inject large quantities of ash and gases into the upper atmosphere, affecting the climate. The Mount Pinatubo eruption in 1991, one of the largest volcanic eruptions of the 20th century, caused global temperatures to drop for a period due to the amount of sulfur dioxide released into the stratosphere. This phenomenon is an example of how seismic activity doesn't just impact the ground but can also influence weather patterns and global ecosystems. Now, consider the possible links between the increased seismic activity and the shifting of tectonic plates. As more and more tremors are recorded globally, scientists are paying closer attention to areas where shifts are subtle but still significant. Regions that are not traditionally earthquake-prone, like the eastern United States, are showing increased activity along fault lines that were previously thought to be dormant. This is creating a new area of concern for seismologists and local governments, who are now re-evaluating their preparedness for potential earthquakes. The New Madrid seismic zone, for example, has been the site of several small tremors in recent years, and scientists are wondering whether this zone, which produced a series of devastating earthquakes in the early 19th century, is once again becoming active. The 1811 to 1812 New Madrid earthquakes were some of the largest in U.S. history, causing widespread destruction and altering the landscape. They also serve as a reminder of the unpredictable nature of seismic activity in the middle of tectonic plates, far from any major fault lines. The ongoing tectonic activity beneath the Earth's surface also raises questions about the stability of other geological features. Could the movement of these plates be triggering the rise of new mountains, or the potential collapse of existing ones? The Himalayas, for instance, continue to rise due to the ongoing collision between the Indian and Eurasian plates, which also results in frequent earthquakes in the region. Conversely, the Great Rift Valley in East Africa, a rift zone where the African plate is slowly splitting apart, is opening up new land and shifting entire landscapes. In the coming centuries, this region could even become a new ocean, and scientists are closely monitoring the shifts in the plates to understand how this process is unfolding. As we reflect on everything we've discussed, it becomes apparent that the recent surge in seismic activity, with over 15,000 tremors recorded in just 1 month, is not just an isolated event. Instead, it's a manifestation of the complex, dynamic processes occurring beneath the surface of our planet. From the ongoing movement of tectonic plates to the possible influence of cosmic events, our Earth is far from static. In fact, it is an ever-evolving and incredibly active system, with each shift, tremor, and eruption offering a glimpse into the immense forces shaping our world. We've explored the fundamental role of tectonic plates in generating earthquakes, with their constant movement driving the geological processes that form mountain ranges, rift valleys, and ocean basins. The interaction between these plates, particularly at subduction zones like the Ring of Fire, has led to some of the most devastating events in history, including catastrophic earthquakes and tsunamis that reshape coastlines and disrupt lives. The 2004 Indian Ocean earthquake and tsunami, for example, was a stark reminder of how seismic events along plate boundaries can have far-reaching, devastating consequences. While large earthquakes and volcanic eruptions often dominate the headlines, it's also the smaller, more frequent tremors that carry significant meaning. These smaller tremors act as vital signals, warning us of the larger, more powerful seismic events that may be brewing beneath the surface. The San Andreas Fault in California, the New Madrid seismic zone in the US, and the volcanic activity of Iceland all point to the unpredictability and danger inherent in the dynamic system of tectonic activity. We've also ventured into the realm of space and its influence on Earth, discussing how cosmic events, such as solar flares, cosmic rays, and even the possible interactions with nearby stars, may have an impact on our planet's geological activity. The Sun's activity, particularly during periods of heightened solar flares, can cause geomagnetic storms that disturb not just our communications and satellites, but could also influence the Earth's crust. While the direct link between solar activity and seismic events remains a mystery, scientists are increasingly interested in how these cosmic phenomena may be affecting Earth's inner workings. Adding another layer of complexity, we looked into how the Earth's core and mantle are involved in these processes. The constant movement of molten rock within the Earth's interior generates the heat and pressure that fuel tectonic plate motion, volcanic eruptions, and the formation of new landforms. The way heat is transferred within the mantle, the flow of mantle plumes, and the interaction between the outer core and the lithosphere all contribute to the ongoing seismic activity. Understanding how these processes work is crucial in predicting future tremors, volcanic eruptions, and shifts in the Earth's crust. The ocean also plays a significant role in the seismic and volcanic activity beneath the surface. Submarine earthquakes, particularly those along the mid-Atlantic ridge, are an integral part of the ongoing creation and destruction of oceanic crust. These underwater quakes often go unnoticed by the general public but have major implications for both oceanic ecosystems and coastal communities. Notably, volcanic eruptions under the sea, such as those in the Pacific Ocean, have led to the creation of new islands and have altered the ocean's landscape. As the tectonic plates shift and new fault lines are formed, the very shape of our oceans may continue to change, leading to further shifts in global sea levels, climate, and coastal geography. Volcanic activity, particularly at hotspots like Hawaii and Iceland, is a fascinating aspect of the planet's geologic history. Volcanic eruptions are often seen as the result of the buildup of pressure in the Earth's crust, caused by the movement of tectonic plates. These eruptions can release massive amounts of energy, ash, and gases, impacting both local environments and global climate. The eruption of Mount Pinatubo in 1991, for example, cooled global temperatures for years, demonstrating how interconnected the Earth's systems are. Additionally, the Himalayas, the world's tallest mountain range, continue to grow as the Indian plate pushes into the Eurasian plate, showcasing how plate tectonics is an ongoing, active process. The oceanic plates and their shifting boundaries also contribute to the formation of new land, with subduction zones often giving rise to volcanic islands. The Mid-Atlantic Ridge, where the North American and Eurasian plates meet, is one such example of a boundary that constantly shifts and moves. Here, magma rises to the surface, pushing the plates apart and causing frequent seismic activity. The increased number of tremors in this area, alongside the volcanic eruptions that occur, could be signaling greater changes within the Earth's crust. This ongoing shift may even lead to new geological features, such as vast new mountain ranges, underwater canyons, and deep rift valleys. The tectonic activity that shapes the Earth's surface is, in many ways, a natural process. Yet, it's becoming increasingly apparent that the intensity and frequency of tremors, eruptions, and earthquakes are rising. Whether due to the natural rhythms of the planet or influenced by external cosmic factors, this heightened seismic activity serves as a stark reminder of just how volatile and dynamic our planet is. As the Earth's crust shifts, it's not just changing the land beneath our feet, but also potentially setting the stage for future catastrophic events, reshaping coastlines, habitats, and human lives. Looking ahead, scientists continue to monitor these seismic shifts closely, trying to decipher patterns and predict future events. The constant movement of tectonic plates, combined with the influence of cosmic activity, suggests that the Earth is entering a new era of geological transformation. Whether we're prepared for the scale of change to come remains to be seen, but one thing is certain: our understanding of the Earth's dynamic nature is more important than ever. As the tremors continue to rock the planet, we can only watch and wonder what will happen next in the ongoing story of our planet's deep, powerful, and ever-changing geological history.